Okay, so thank you very much. I'm honored to be part of this meeting, the only non-Russian invited to present here. Sasha Nanin was my colleague for many years at the University of Campinas, and I have good memories of him, especially interacting with students. I have some good friends that studied with him and who also have very fond memories of him. So I decided to speak on this meeting about. Maybe I can do this as well. Yeah. About some recent work I've done with Aron Simis and Abbas Nejad. This is on the archive. The archive version is the purely commutative algebra version of this work. The other name that I have down there, Daniel Futata, was my PhD student. And in his PhD thesis is the algebraic geometric version, the sheaf theoretical version of what I'm going to present today. So today I'll present the more sheaf theoretical version that it's the one I'm more comfortable with. But everything that I'm going to say here, has parallel results in purely commutative algebraic terms. Okay, so let me start with the setup here. So R is this ring of homogeneous polynomials. Okay, so K is some field, and overall I'm going to assume that the characteristic of the field does not divide the degree of a particular polynomial. So F, I'm choosing to be a homogeneous polynomial of degree d plus 1. And then we can consider the gradient of this polynomial as a morphism, either as a graded map of R modules, right, from 3 copies of R to R shifted by D, or as a sheaf map, right, as from the structure sheaf of P2 to the shifted or twisted P2. Then one can check that if F is a square free, by that I mean that there's no polynomial h such that h square divides F, right? So that's what I mean by square free. Another way to say this is the curve, the plane curve associated with F is reduced. So F is square free if and only if the partial derivatives have no common divisor. And then the image of this morphism, this gradient morphism, it's an ideal sheaf, right? So it's a subsheaf of OP2 twisted by D. So it's the ideal sheaf of some scheme, and this scheme is the Jacobian, called the Jacobian scheme, right? So this Jacobian scheme J sees the singularities of the curve F equals 0. So if there are any questions, feel free to interrupt me. Because while I see the talk, I cannot see the app here. In the sheaf theoretical version of things, we take I'll take what's called the logarithmic tangent sheaf associated for the curve F, that I denote by TF. This is the sheaf whose sections are the vector fields on P2 that are tangent to the curve. So at the points of the curve F equals 0, the sections of this sheaf, or these are vector fields that are tangent to the curve at the points of the curve. In commutative algebra terms, this can be described as a module of derivations. You take all the derivations of the ring R, of the polynomial ring, that cancel F, right? Cancel the polynomial F. Another way to say that is you take 3 homogeneous polynomials of the same degree for which this equation here holds. So in other words, you can think of this H as being a syzygy for the matrix or the vector nabla F. So this sheaf TF is always locally free. You can think of this H as syzygies of nabla F. And we have always this so-called Euler derivation as well, right? So the Euler derivation is something that does this, that the Euler derivation applied to F is just the degree of F times F. This is where the hypothesis that the characteristic of the field does not divide the degree of F.
Sorry, could I ask you?
Sure, yes.
Some short question on the slide before. Just please, could you remind why it's locally free? It's a corollary of the fact that all singularities are plane, or something simpler.
Yes, this is because we are in the plane. So in general, in arbitrary dimension, this TF would be reflexive sheaf.
Okay.
Right? It's a reflexive sheaf because it's the kernel of a locally free sheaf. So TF is the kernel of this morphism here.
Yeah.
Right? So it's always a reflexive sheaf. But in dimension 2, every reflexive sheaf is locally free. Right? Okay?
Thank you. Yeah.
Thanks. And then we say that the curve X, that I'm denoting the set of zeros of F to be this plane curve X, this curve is said to be free if the sheaf, the logarithmic sheaf, splits as a sum of line bundles, or which is equivalent to say that this module of derivations, that there 0F, that I introduced here in the previous slide, right? So this there 0F module is free as a graded R module. And this is a theory that goes back to a paper by Saito in the early 80s. So it's already a 40-year-old theory, has lots and lots of literature, both in algebraic geometry and in commutative algebra. And some of the questions that are asked is how can one characterize free curves, right? So what are the properties that the free curves have? And in particular, there is this important conjecture by Terral that says that the freedom of a line arrangement is determined by its combinatorics. So what do I mean by that? So a line arrangement you can think of as a plane curve. So it's the case where this F is just a product of polynomials of degree 1. So when F is a product of a bunch of polynomials of degree 1, this means that the curve X will be a bunch of lines intersecting one another on the plane. So that's what is called a line arrangement. And then the combinatorics of the line arrangement is just encodes the points and how many the points of intersections of the various lines and how many lines pass through each point of intersection. So Terral's conjecture says that a line arrangement is free. The statement of the Terral conjecture essentially says that a line arrangement is going to be free. You can tell that simply by looking at the combinatorics, not at the particular position of the lines, but simply how they intersect one another. And this conjecture, I think, is proved up to 13 or 14 lines, but it's open in general. So let me give you two simple examples. So one is this genetic arrangement of 3 lines. So have F to be this polynomial of degree 3. Then one can check that the gradient of F has 2 syzygies that I'm denoting here by nu1 and nu2. These are 2 syzygies of this vector here. The Jacobian scheme has precisely 3 points, which are the 3 points of intersection. And then using this, the fact that it has 2 syzygies of degree 1, you can tell that the logarithmic tangent sheaf is just a sum of 2 copies of O minus 1. So in particular, this genetic line arrangement with 3 lines is always free. And this is a result that is actually false when you have 4 or more lines. So genetic line arrangements will never be free if you have at least 4 lines. But for less than 3 lines, they are free. So another example that goes in the opposite direction is that smooth curves are never free, except for the line. So except when the degree of f is 1, smooth curves will never be free. And in fact, more is true. Not only the logarithmic tangent sheaf does not split as a sum of line bundles, but the log tangent sheaf is actually a mu-stable bundle. So in the last line here, I just remind what is a mu stability for a vector bundle in this context. It means that any line subbundle of the log sheaf has degree smaller than half of the degree of the log sheaf. So it's stabilities abound on the slope or the degree of subline subbundles. Right, so any questions?
And well, I just want to understand, is it clear what kind of curves are free? For example, stable curves, I just offer some conjecture.
So I'm not sure I understood. So,
well, I just want to understand, is there a criterion of a curve to be free, except that conjecture you explained before?
Oh yes. Yes, there are criteria. I'm not sure. Yeah. So if by the end of the talk I don't give you a criteria, I'll find a way to write one. Right? But there is something called the Saito criterion.
Okay.
That tells you, you make a matrix, you make a 3x3 matrix with 2 syzygies for the nabla f plus the Euler derivation. Right? So you take 2 syzygies and the Euler derivation. If the determinant of this matrix is a multiple of the polynomial itself, then the curve is free. Right? This is actually an if and only if statement. The curve is free if and only if this matrix, consisting of 2 syzygies plus the Euler derivation, has determinant a multiple of the polynomial itself. Okay. Was it possible to understand the?
Yes.
Yeah. It's very simple, very nice criteria.
Yeah.
And then in commutative algebra, there are other criteria. So if the Jacobian scheme is a perfect ideal of height 2, then the curve is free. There are several criteria in the literature.
But is it possible that irreducible curve is free? Yes, irreducible.
Yes. The first example.
Irreducible singular curve, yes?
Yes. And the first example occurs in degree 5.
5, yeah.
Okay.
Because here you have curve of degree 3, but it is reducible.
Yes. Well, there is also the case of a line, right? So just a line this is free of degree 1 and it's irreducible. But the line is boring. So
that's yeah.
But yes, you can also have irreducible singular curves as free curves. More questions? Yeah. And one question that is not so studied in the literature, but it's important for people like me and my colleagues that like stable bundles, is when is the log sheaf stable or semi-stable in the sense that I mentioned in the previous slide. There's actually a theorem, a criteria for mu stability that in this context of plane curves was proved by Dinka. And then in higher dimensions, there is a version for Daniele Faenzi and Simone Marchesi. And they say that suppose, well, a curve will only have isolated singularities, right? So if the number of singularities counted with multiplicities and so on, so if the number of singularities of a curve is small compared with the degree, and this is the precise formula here for the degree. So if you have a small number of singularities, then the log sheaf is mu stable. And mu stable sheaves cannot be free, right? So if you so mu stable bundles never split as a sum of line bundles. Okay, so if you have a bundle that splits as a sum of line bundles, you always have a subbundle violating this inequality. One of the factors will violate this inequality here, right? So stability is in some sense opposite to freeness. So this means that this moral here, right? So free curves must be somehow very singular. So a free curve must have lots of singularities in some sense, right? So lots with regards to this inequality.
Excuse me. So sure. The number of singularities is always less or equal than d times d minus 1 times d minus 2 1/2. Yes.
Yes. This is
so it's very close to this estimate. So it's approximately d squared, 1/2 of d squared in both cases.
Yes.
So it's not very rough requirement on the number of singularity. Am I right?
No. Yeah. So so this number is large, right? Relatively large.
Mm-hmm.
Because it grows like d square. Right? So and this is d over 2 is actually the integer part, right? So of d over 2 here.
Mm-hmm.
Okay. And one other fact.
Sorry, what is the year of this result?
Sorry?
What is the year of this result?
Oh, Dinka's, I don't know, but the Faenzi Marchesi is recent. It's a paper by 2021 or 22. Mm-hmm. And Dinka's is probably from the 90s. Dinka's result is older.
Mm-hmm. Okay. And you mentioned the result in higher dimensions. It's also a free result or not?
Yes, the Faenzi Marchesi paper works for higher dimensions. Okay. So if you have, you can do everything that I've said here for hyper surfaces, right? Oh. So if you have a divisor in PN, you can define the logarithmic tangent sheaf for this divisor. Okay. And this result says, so suppose your hypersurface only has isolated singularities.
Okay.
So if the number of singularities is small relative to the degree in this sense, then the log sheaf is mu stable.
And what is the effect? I mean, what is important in the result? The Horenstein property of singularities or not?
No. So this is about stability. So really, it's looking at the degree of all possible line subbundles. So the number of singularities, how non-singular a curve is, restricts the degree of the syzygies that nabla F can have. Right. So this might be clear in a couple of slides.
Okay.
And one thing that I like to point out is that this bound is not sharp, right? So one can find quartic curves that violate this bound, but whose log sheaf is still mu stable. So there might be room for improvement in this bound, in this result. Okay. More questions? So the goal of our work, so what we try to add to this literature is trying to answer this question, right? So what lies between smooth and free curves? So smooth curves are never free. So there might be a way to tell how non-free a curve is, right? Measure the lack of freeness of a curve. And this is done via this diagram here. Let me try to explain this diagram. So this nabla f here is our Jacobian morphism here. Okay, so this is the morphism that I put in the first slides, just the partial derivatives of f. Then the ideal sheaf, this ideal of the Jacobian scheme, is the image of this nabla f. Okay. Now, age, as I mentioned a few slides ago, is a syzygy. So it's something that when you compose with nabla f, gives you 0. So this composition here of age and nabla f vanishes. This means that this induces, this map age here factors through the kernel of nabla f, right? So this gives you a section of the logarithmic tangent sheaf, a global section of this twisted log tangent sheaf. That's what I'm denoting by sigma here. And then you can look at the co-kernel of this section. Co-kernel of this section will give you an ideal sheaf as well. Right? So this is the ideal sheaf of some zero-dimensional scheme in P2. This is what we call the Bourbaki scheme, associated with the curve and the syzygy. And this scheme tells you the zeros of this section. It's the scheme of zeros of sigma, right, as a section of the logarithmic tangent sheaf. And we also obtain this sheaf Q here as the co-kernel of this morphism H, which can be written as the extension of these two ideals, the Jacobian ideal on one hand and the Bourbaki ideal, the Bourbaki scheme on the other hand. Okay. Any questions about this diagram? Yeah.
Okay.
And
A is what is A? How we can choose A? This for this syzygies in the upper line.
A in principle is free. It's
free, yeah?
Yeah, it can be anything. For sake of this diagram, A is anything, right? So we know that if A is big enough, we always find syzygy.
Okay. Thank you.
More questions? Yeah, so for this diagram, A can be anything. And one formula that you can show is actually not very hard to see that what I'm denoting here by H0 of OB. OB is the structure sheaf of this zero-dimensional scheme, and the same for OJ. So H0 of OB and H0 of OH are the lengths of these two zero-dimensional schemes. So the number of points in the schemes B and J counted with multiplicity. And the sum of these two schemes, the length of these two schemes, is just given by this formula that only depends on the degree of F and the degree of the syzygy. Right? So the scheme itself, B, depends on the choice of the syzygy, but its length only depends on the degree of the syzygy. So one way to get rid of this dependence on the syzygy is looking at what is called the initial degree in commutative algebra. So the smallest, the minimum possible degree for a syzygy of f. So the smallest possible degree of an element in this module of derivations, or the minimum possible twist for which the log sheaf admits a section. So this perhaps related to the previous question, you can take that A to be the smallest possible degree of a syzygy. And observe that E is always smaller or equal than D. Because you always have the Koszul derivations, right? So for the, it's a pity that I don't know how to write here, but you can. There's always a cheap way to find a derivation, which is take a vector which just inverts the position of two partial derivatives and changes the sign of one of them. So you can take, for instance, minus partial of f with respect to 1 on the first entry, and then partial of f with respect to 0, del 0 f in the second entry of the vector, and 0. So that would be a syzygy of degree D. So these are the Koszul derivations. So since you always have these Koszul derivations, this initial degree is always smaller or equal than D. Right? So remember, the degree of f is D plus 1. And what we call the Bourbaki degree of the curve, this is our definition now, the Bourbaki degree of the curve is the length of the Bourbaki scheme when you take a derivation of smallest possible degree. And this quantity, this number, the Bourbaki degree of a curve, will actually only depend on the curve and not on the particular choice of derivation of minimal degree that you choose. And this formula here on the top can then be rewritten in this way. So the Bourbaki degree plus the Tiurina number for the curve is always given by this formula here, involving the degree of the curve and the initial degree. So the smallest possible. Yeah.
What is, you said Turing number, or what? Turing number?
Tiurina number. So the Tiurina number is precisely this, the length of the Jacobian scheme.
Okay.
Right. So it's something that only depends on the singularities of J. Right. I don't know if people here are familiar with this this theory, but there is something called the local Tiurina number, and then the sum of all local Tiurina numbers is this global Tiurina number for the curve. Right. But this is essentially the the sum of all singularities of the curve, counting with some multiplicity. Okay. Is that okay? More questions? Good. So some facts about the Bourbaki. So the Bourbaki degree is always between 0 and e squared. So e is the initial degree for the curve x. And it, in some sense, characterizes free curves because the Bourbaki degree is 0 if and only if the curve is free. And on the other hand, the maximum possible value of a Bourbaki degree is d squared. And that happens precisely when the curve is smooth, right? Because when the curve is smooth, the initial degree will be precisely the Koszul derivations, like the module of derivations will be generated by the Koszul derivations, the 3 Koszul derivations. So when the curve is smooth, this E is precisely equal to D. And the Bourbaki degree attains its maximum possible value, which is d squared. Right? So The Bourbaki degree, in this sense, precisely measures. It's a measure between being free, which is the smallest possible value of the invariant, and being smooth, which is the largest possible value of the invariant. And one result that we managed to prove for something in the middle is that the Bourbaki is d squared minus 1 if and only if the curve has only one nodal singularity. Right? So the mildest possible of singularities, which is a one nodal singularity. This is for D. D here, I should have written D here has to be at least 2, I think, for this if and only if here occurs when D is at least 2.
And what's about one cuspidal singularity?
Then this we don't know. So only one cuspidal singularity has Turin a number equal 2. But it's not true that the Bourbaki it's going to be d squared minus 2. Right? For instance, a cuspidal, the Bourbaki for a cuspidal cubic is 1, not 2. Right? So if this formula was true for cuspidal curves, a cuspidal cubic would have Bourbaki equals to 2. But it's not. It's equal to 1. So we don't have a formula for one cuspidal. Right? What is true is that if a curve has n nodal singularities, then the Bourbaki is d squared minus n. But we don't have a reverse for that, right? So if the Bourbaki degree is d squared minus n, that doesn't imply that it has n nodal singularities in general. Did I answer your question?
Yes, thank you. It's clear, but strange.
Yeah. Yeah, I agree. We tried for a while to show that, Bourbaki is d squared minus 2, if and only if it either has 2 nodal singularities or it has cuspidal curve.
So it means that, for example, degree of the smooth curve is related with the genus of the curve, yes? And we have also the arithmetic genus, which encodes also some measure of singularity. So after your answer, that we have that this Bourbaki degree is not well behaved with the arithmetic genus, yes? Because
with arithmetic genus, yes.
It's not very good, yeah.
We haven't really looked at it, but I don't think it is.
Okay.
Right? Yeah. One could think more about this, the relation between the Bourbaki and the genus. But I'm not sure what to tell you. Okay. So one way to interpret the meaning of this Bourbaki scheme is the following. If you take a syzygy, H, you can look at the common zeros of the 3 polynomials in H. That will give you a bunch of points. Typically, that will not be empty, and it will give you a bunch of points. And the Bourbaki scheme will always satisfy this formula here. So the Bourbaki scheme is always contained in the zero set of the syzygy. And the difference between the Bourbaki scheme and the zeros of the syzygy is always contained in the Jacobian scheme. This means the following. So, sorry, my slides has a problem here. I'm not sure you can. Yeah, okay. So one way to interpret the Bourbaki scheme is the following. So if you look at a vector field in P2 that is tangent to the curve, at the points of the curve, this vector field will have zeros on the singularities of the curve, right? Because the singularities of the curve are precisely where the tangent vector to the curve vanishes. But this vector field may also have some zeros away from the curve. And these zeros of a tangent vector field away from a curve are precisely the Bourbaki scheme. So the Bourbaki scheme tells you, gives you the zeros of a vector field that is tangent to the curve, which do not lie on the curve. That's the geometric interpretation of the Bourbaki scheme. And from this formula here, since B is always contained in S, right, so this means that if X, if the curve admits a regular syzygy, so a syzygy for which this H 0, 1, and 2 form a regular sequence, then it's got to be free. Right? So this is one characterization of a free curve. So if it admits a syzygy with no common zeros. And when this scheme of zeros, both the Jacobian scheme and the scheme of zeros for S are reduced, so just a bunch of isolated points, then the Bourbaki scheme is precisely this difference. This is the these are all the zeros of the syzygy that do not lie on the curve. That's my last formula here. And one more geometric result that that'll finish my talk is this one. So if you take the set of all curves of a given degree in a given Bourbaki degree, think of this as a subset of the projectivization, right, of all curves. So this is the set of homogeneous polynomials of degree d plus 1. So in the projectivization of this vector space, you look at this set, all the curves with a given Bourbaki degree, and these are locally closed. So these are algebraic sets. And in particular, the set of all free curves is algebraic as well. So this was something that was not in the literature before, as far as I could tell. People were studying individual, the freeness of individual classes of curves, but never tried to study the variety, right? The set of all free curves. And then this poses new questions for which I have no answer, right? I really don't know how to approach these questions, except for some very simple cases. So what is the dimension of this set of all free curves? And what are the reducible components? So try to study free curves as a whole, right? So as an algebraic variety. So that's the new direction that I for research on this area that I'm proposing here. Okay. So there are So actually, my last slide here is this. Mention that there are all sorts of generalizations, right? So everything that I said here, except for the Bourbaki degree, right? So the business about freeness of curves can be generalized to hypersurfaces in PN. Actually, there's a newer result, a newer paper of mine with Daniele Faenzi and Jean Vallès that also tries to give a generalization for this theorem for subschemes of codimension larger than 1. One can also try to consider the Bourbaki degree and the freeness of divisors and subschemes in other projective varieties that are not just the projective space. And we've been trying to do something with toric varieties. And also there is a question how the symmetries of X, the curve, interferes with the symmetries of the modulo of derivations. And if there are some symmetries also in the associated Bourbaki schemes. Right. So thank you very much for your attention and for the possibility to give this talk. Thank you.
Thank you very much, Marcus. Dear colleagues, are there any questions?
So everything here doesn't depend on the base field except for this degree and characteristic condition. Yes, so everything works for finite fields or for anything. Yes.
Yes. As far as I can tell, yes.
Thanks.
Okay, and I have a question. And when you say that it is, so you have the slide, that it is algebraic set. So it means algebraic that it is, you consider only, so on the coefficients, yes? It satisfies some algebraic relations, yes? Without, you don't consider the action of PGL2 group, yes?
Yes. No. There is no action, no quotienting by the automorphisms of this projective space here.
Okay.
So this means that
only on coefficients.
As you said, being free or being having a fixed Bourbaki degree is a polynomial are polynomial conditions on the coefficients of the polynomial f.
Okay. Thank you.
And what is the proof of this theorem?
Yeah, so
at least
the proof. Yeah, so our proof is. Let me. Yeah, so if you look at this exact sequence here, means that we can look at this morphism here as a quad scheme, right? So there is a quad scheme involved. So it's the quad scheme of 3 copies of O with some fixed Hilbert polynomial, which is the Hilbert polynomial of a of the ideal sheaf of some 0-dimensional scheme. Right, so the TF, you can think of these Fs with a given Turina number, with a given Jacobian scheme, to be elements in a quad scheme. And then we use this formula here, so that once the Turina number is fixed, so the Bourbaki will only depend on E, on the, sorry, the Bourbaki will only depend on the initial degree, and the initial degree is upper, maybe lower semi-continuous. So the smallest possible. So each time I fix the initial degree, I'm fixing either a closed or an open set within this variety of curves with fixed Turina number. So it's always going to be some closed or open set in some quad scheme, which you know is a projective variety that lies inside this our projective space. Right?
Okay.
Yeah, maybe I'm not sure it was too clear, but
no, it's thank you. Yeah, okay.
So if you want more details, I can share.
No. Yeah, thank you. It's okay. Yeah,
that's enough.
It's clear. Yeah, and then I can read it.
Wait, are there another questions? No, let's thanks again to Jardim.
Thank you, everyone, for your questions. This was a great talk, with very interesting questions.
Okay, dear friends, tomorrow we will continue at 10 o'clock in Novosibirsk time. The first talk will be by Yefim Zilmanov. So, see you tomorrow. Bye.
Sorry, Marcus, could I ask you just, is it written somewhere like this in this style? I looked at your last paper on archive. Is it written there?
No, this algebraic geometric version with sheaves and all, it's not on the archive. It's just my student's thesis. What is in the archive is this paper that I mentioned in the beginning with Aron Simis and Abbas Nejad, which is in just about modules and it's commutative algebra, right? So this is on the archive.
Thanks.
But it will take me. My students' thesis is in English, but it's not particularly well written. So if you want, I'll be glad to share that his thesis as well. Right?
Thank
The
you.
language is not important now because we have a Google translator.
Oh yes, and then the it's more important to be well written than written in whatever language, right? But yeah.
Right.
But if anyone is interested, you can send me a message, and I'll be happy to share my students' thesis.
Okay, thank you very much again. Bye.
Thanks, everyone. Bye-bye. Have a good meeting tomorrow.